Right. So today we'll discuss the idea of heat, temperature, the difference between heat and temperature, and how temperature can be measured. Okay, basically how thermometers work and all. What are different types of thermometers? What are the different temperature scales? Okay, we'll be discussing those things. Any doubt you have anywhere, you can just unmute and ask, or you can type in chat also. Fine. Can any of you tell me what is heat? Like, just tell whatever idea you have. What is heat? Fine. It is correct that it's a form of energy. But you would also be knowing that there are many different forms of energy, right? Like one of them is heat, you might have studied, the light, sound, okay, mechanical energy, chemical energy. There are many different forms of energies. How do you differentiate heat from other forms of energy? Like how is heat different from the other forms? Any idea, anyone? Like whatever idea you have, you can share, no problem. How is this form of energy, heat, different from other forms of energies? Fine. I got one answer as heat is a measurement of temperature. This is actually not really correct. Heat is not a measurement of temperature. You can say the reverse. Temperature is kind of measurement of heat, but also that is also not completely correct. Okay. So how is heat different from other forms of energy? Is basically heat is a form of energy which can travel from one place to another. Okay, which can flow from one place to another, and it flows usually whenever there is a temperature difference. Okay, so basically it's a form of energy which flows when there is a temperature difference. Okay, see, it's difficult to give the perfect definition of heat actually. Okay, there is a temperature difference, heat can flow, but heat can also flow when there is no temperature difference also. Okay, you will learn. Okay, in this chapter itself you will learn. Fine. Since it's a form of energy, obviously its units will be same as those of energy. Can one of you quickly tell me what is the SI unit of energy? SI unit of energy. Okay, joule, correct. So heat will also be usually measured in joules itself, which is basically kg meter square per second square. 1 joule is 1 kg meter square per second square. Dimensional formula also you can write. But there are some other units of heat which are frequently used. One such unit is calorie, denoted by Cal. Calorie is actually a very old unit of heat. Okay, the unit which they used to use before the SI system came into place. Okay, but it's still quite significant calorie. And 1 calorie is approximately 4.2 joules. Okay, it's close to 4.18 joules. We'll usually approximate it to 4.2 joules. So calorie is a bigger unit than joule. Fine. And CGS unit, like SI unit is joule, kg meter square per second square. The CGS unit, can any of you tell the name of the CGS unit of heat, which is basically gram centimeter square per second square? What is the name given to this? You all must have studied this in your 9th and 10th classes, maybe. Okay. CGS unit is called erg. Fine. And if you convert 1 gram, or let's convert joule to erg. 1 kg is 10 power 3 grams. 1 meter is 10 square centimeter, 100 centimeters. So if you square it, it becomes 10 power 4 centimeter square. Per second square remains as it is. So basically, 1 joule is 10 power 7 gram centimeter square per second square. So you can say 1 joule is 10 power 7 ergs. Fine. So these are some common units that we use to express energy. Okay. For heat, like as far as your syllabus is concerned, we'll be mostly using joule and calorie itself. Okay. So basically, heat is a form of energy which can flow from one point to another or one object to another when there's a temperature difference. What is temperature then? Any idea, anyone? According to you, what is temperature? Fine. So one answer I got is measurement of heat in an object, and another answer I got is measurement of degree of hotness or coldness also you can say of an object. Okay. The second one is more appropriate. Okay. You can't say temperature is a measure of heat. Okay. See, let me give you some idea. Okay. Uh, Consider 2 cups of water or fine, 2 containers of water. Let's say one of them is a small cup. Small cup obviously would have fewer molecules of water. Okay. Less amount of water. And another one, let's say, is a large barrel of water. Okay. Or a tank of water, you can say. Obviously, it contains more number of molecules of water, more amount of water. Let's say these two are at room temperature initially. Okay. Let us approximate it to some 25 degrees. Okay. Both of them are initially at, I mean, water in both containers is initially at 25 degrees C. Now, see, we are talking about what is temperature, but we are already using temperature. I mean, how do we say they both are at same temperature? Basically, when we touch them, we feel the same. Okay, so we can say that they are at same temperature. Okay. Now you supply heat to them. Okay, you put them both on a stove, which provides the same amount of heat to each container. Okay. So let's say you put it on flame, rough diagram. And let's say the same amount of heat is supplied to both of them for the same duration of time. Right? Let's say for 5 minutes you put them on the stove. Both burners are identical. Okay. After 5 minutes, which container will have higher temperature? From your everyday experience, you tell me, will the cup of water feel hotter or the large barrel feel hotter, or will they still be at same temperature after heating for 5 minutes at the same rate? What do you think? Okay, all of you have given the same answer. Good. If they are initially at the same temperature and you provide the same amount of heat to them, you will feel that, I mean, not you will feel, you will observe that the smaller cup of water will go to a higher temperature than the bigger one. Okay, so maybe after heating for some time, the smaller one's temperature may rise to some 45 degrees C, but the bigger one's temperature only rises to, let's say, 35 degrees C after supplying the same amount of heat. Okay, and this is true. Fine. Now you see, we supplied the same amount of heat, but one of them is finally at a higher temperature than the other. Okay, so temperature is not directly a measure of heat. Right? That is what I wanted to show you. I wanted to show you the difference between heat and temperature. Both systems are given the same amount of energy, but both systems don't show the same temperature. Okay, so what is temperature then? Temperature is basically a measure of heat supplied per molecule, okay, or heat per molecule. I'm not saying it is exactly equal to heat contained in each molecule. It is a measure of that, okay, or it is proportional to that, you can say. So temperature is not a form of energy. Okay, temperature is not direct measure of heat, it is proportional to heat per molecule. Okay. So see, we supplied the same amount of heat. First system had less number of molecules, let's say small n number of molecules. Second system had a large number of molecules, capital N. Okay. Then how much heat was received per molecule? In the first system, it is heat divided by small n. Okay. How much ever heat we supplied divided by small n. In the second system, which is it is the same amount of heat divided by a greater number of molecules. Now the denominator is greater in the second case, so temperature will be lesser in the second case. Okay. So temperature depends on the heat available per molecule. Okay. Heat supplied per molecule, removed per molecule, or available per molecule. Okay. Whereas heat is basically the total energy contained in the system. Okay. Total energy given to both these systems was the same, but per molecule, the smaller system gets more heat. Okay. So hope you all understood some basic difference between heat and temperature. What is the SI unit of temperature? And what are the other units you can think of? Tell me what all units you know of temperature. Fine. The SI unit of temperature, as you all are aware already, is Kelvin, denoted by the symbol capital K. And let me just remind you that temperature is a fundamental quantity, okay, fundamental physical quantity according to the SI system. Fine. SI unit is Kelvin. It has its own dimensional formula, capital K. Sometimes they even use theta to indicate temperature. That's fine. Okay. Some other units of temperature are degree Celsius, degree Fahrenheit. Okay. There are many other units as well. We will only be interested, we only need to study these three units and how to convert one from the other. Fine. How is temperature measured? Basically using a thermometer, right? Can any of you tell me how a thermometer works? Like whatever thermometer you know about, just recollect and tell me how you think it works. Okay, if you want, you can unmute and tell, otherwise type. Okay. Uh, Mercury thermometers are quite common. They are based on expansion of mercury, correct? So basically, expansion of mercury when temperature is increased. Okay, that is one kind of thermometer, mercury-based thermometers. But these days, non-contact thermometers are quite common. Mercury-based thermometer requires contact. Okay, you have to place that thermometer in contact with the body. Only then you can measure the temperature. These days, there are non-contact thermometers also. You just point it at the object and click. It will show you the reading of the temperature. That kind of thermometer works based on radiation. Okay, it senses the radiation emitted by the object, and from that it can estimate the temperature. That also we will learn in this chapter itself when we talk about heat transfer through radiation. Okay, for now we will discuss how mercury based thermometer works and how to calibrate one and how to take readings from mercury thermometer. Okay, so basically in earlier days itself they knew that materials expand when their temperature is increased. Okay. And mercury shows significant amount of expansion at common temperatures like room temperature and temperature slightly higher and lower than room temperatures. Mercury shows a lot of expansion and contraction, right? So just a moment, let me show you an image of a thermometer. We'll discuss how the mercury thermometer works. There are different temperature scales, no Celsius degrees, Fahrenheit degrees, okay, and some random degrees also you can make. How to convert from one to other, we'll be discussing. Okay. Right. So consider a common thermometer like this. Basically, it is made of glass, and inside the glass tube, there is a column of mercury. Okay. So mercury actually looks silvery in color. Okay. Steel, silver, mercury, they all look almost the same. Here they have indicated in red, let it be. So that red liquid that you see inside, or red column that you see inside, is a column of mercury. Fine. Now, in olden days, Okay, when they invented the temperature scale, Celsius scale or Fahrenheit scale or some other scale, when they invented those scales, it was known that melting of ice, okay, and boiling of water happened at particular temperatures. Fine. So these two processes, basically melting of ice and boiling of water, were used as the references. Okay, the temperature at which ice melts was taken as one reference temperature. The temperature at which water boils was taken as another reference temperature. Okay, so what they did is they took a column, glass tube like this, poured some mercury in it. Okay, of course, they must have tried out a lot of materials and finally arrived or concluded that mercury is best, okay, to show variations in temperature because it easily expands and contracts at common temperatures that we come across. Okay, so they took a glass tube, poured some mercury in it. Uh, they immerse this glass tube, basically, they immerse the thermometer in melting ice. Okay. When they immerse the thermometer in melting ice, the mercury column that is there inside the thermometer, it assumes a particular length. Okay. It won't be zero length. It will occupy some space in the thermometer. Okay. So let us discuss how the Celsius scale was created. So this scientist Celsius, basically what he must have done is that when the thermometer is immersed in melting ice, as that melting process is going on, you have to put the thermometer there. At that time, okay, or at that temperature, I should say, the length of mercury column, let's call it L naught, okay, or L0 also you can say. And he called that temperature, okay, the temperature at which ice melts, okay, Celsius called that temperature as 0 degree Celsius. Okay, on the thermometer or on the temperature scale that Celsius invented, he called the temperature at which ice melts as 0. Okay, we'll take this temperature as 0. That is what he decided. Okay. Then what must have happened? Like after that, what he must have done is taken this thermometer and placed in boiling water. Okay, as that process of boiling is happening. Okay, boiling means what? Water getting converted to steam. Okay, as that process is happening, the thermometer was immersed in water. Okay, then obviously boiling of water happens at a different temperature. At a different temperature, the mercury occupies a different amount of length. Fine. So he allowed the mercury to expand. Must have allowed the mercury to expand. And the length assumed by the mercury column when it is placed in boiling water, let's call that length as L100. Okay. Why? Because Celsius chose to call that temperature as 100 degrees Celsius. Okay, that was their choice. They were the ones who invented the scale, so they could have called it any, they could have given it any number. So the temperature at which ice melts, Celsius chose to call it as 0. The temperature at which water boils, Celsius chose to call it as 100 degrees. Okay. So at 0 degrees, the mercury column occupies some length, which is L naught from here to here. At 100 degrees, okay, on the Celsius scale, the mercury column occupies or assumes a different length, which is basically longer, definitely longer, and it is from here to here. Okay. Now, there is an assumption we make. The assumption is that the length of the mercury column, okay, length L, varies linearly with temperature. Okay. If any one quantity varies linearly with another quantity, for example, if y varies linearly with x, okay, varying linearly means what? When you plot a graph, no, it will be a straight line. Okay. What is the general equation of a straight line? Y is equal to mx plus c. Okay. There are many other ways also to write the equation of a straight line. Some of you might have studied the two-point form of a straight line, slope intercept. This is slope intercept form. M is the slope, C is the intercept. Okay. Slope point form is there, two-point form is there. There are different forms of writing the equation of a straight line. But when one quantity varies linearly with another quantity, This is how the equation between them will look. Okay, powers of both quantities in the equation will be 1 and 1. Okay, the 2-point form of the line will be written like this: y minus y1 by y2 minus y1 will be equal to x minus x1 by x2 minus x1. Fine. Or if you want the slope point form, I think it will be written like this: y minus y1 is equal to m into x minus x1. If I remember correctly, I think this is how it is written. Delta y by, yeah, correct. Fine. So these are the different ways in which you can relate two quantities or two variables which vary linearly with each other. Okay. The power of y is 1, the power of x is also 1. So it was found experimentally that length varies linearly with temperature. It's not an assumption actually. Experimentally, they have determined that length varies linearly with temperature if you keep the area of cross section constant. Okay. Now, at 0 degrees on the Celsius scale, the length is L naught. Okay. At 100 degrees on the Celsius scale, the length of the mercury column is L100. So at different temperatures, there are different lengths. And we know length varies linearly with temperature. Now, what is our aim? Our aim is to determine temperature based on the length of the mercury column. Like when you immerse this thermometer in some other system, based on the length of the mercury column, you should be able to tell the temperature. That is what we want. Okay. So length is the known quantity here. Okay. Length of mercury column, you can literally see and measure. Okay. From length, we want to estimate temperature. So length is the known variable. Temperature is the unknown variable. Okay. Known variable will be taken as x. Unknown variable will be taken as y. Usually that is how we write equations. So let's call length as x and unknown variable temperature as y. Now temperature varies linearly with length. Length varies linearly with temperature. Temperature varies linearly with length. So y varies linearly with x. Then the equation between temperature and length should be of this kind. One of these types. Okay, you can write it in whichever way you want. But length and temperature should be related this way. So what Celsius did was, see, he knew two lengths at two temperatures. So it's like knowing x1, x2, and y1, y2. Okay, so it's like we know 2 points. We know the coordinates x1, y1. Okay, that means we know the length at 0 degrees. And we know the coordinates x2, y2. We know the length at 100 degrees also. What do we want to estimate? We want to estimate temperature based on some other length. Okay, so we need y value at some other x value. Okay, so we need an equation between y and x. So since we know 2 points, we will use the 2-point form of the line. Okay, y minus y1 by y2 minus y1 is x minus x1 by x2 minus x1. We are going to use this formula to relate temperature and length. That's all. Simple idea. Okay, if you know two lengths at two temperatures, you can tell temperature at any other length by using this equation. Now, what are we considering as y? Y is the temperature, unknown variable. X is the length of the mercury column, known variable. So what we will do is we will write this equation accordingly. Y is temperature minus initial temperature is T naught. That is 0 degrees. Okay, you can write it as 0 also. Divided by final temperature is 100 degrees, which is literally 100 itself, minus again T naught. Initial temperature is 0, is equal to length minus initial length divided by final length minus initial length. Okay. So when the thermometer is immersed in melting ice, he called the temperature as 0. He recorded the length as L naught. So that gave us one set of coordinates, x1, y1. When the thermometer is immersed in boiling water, he called the temperature as 100 and recorded the length. That gave us another point, x2, y2. Okay. Now, if you know x1, y1 and x2, y2, you can generally relate x and y like this. So the numerator changes to t, denominator becomes 100 is equal to L minus L naught divided by L100 minus L naught. So send the 100 to the other side. You get t is equal to 100 into L minus L naught divided by L100 minus L naught. So what will this formula help you with? This formula can help you calculate the temperature if you know the length of the mercury column. That's all. So you put the thermometer in some other in some other system. Okay. the column will expand to some length. It may not be at L naught, it may not become L100. It'll occupy some length. Based on that length, you can tell what is the temperature of that system. So this you can say is the working formula of the Celsius thermometer. Fine. So did you all understand any doubt in this? At 0 degrees C, let's say the length of mercury column was 2 centimeters, okay, in the thermometer. At 100 degrees C, that means when immersed in boiling water, let's say the length of the mercury column was, let's say 22 centimeters. Okay. I want you to estimate how much is the temperature when the length of the mercury column is some 5 centimeters. Okay. Try this, all of you. I'll give you 2 minutes to solve. Okay. I got 4 answers as 15 degrees and 1 answer as 30 degrees. Let's see. So as I said, it's like knowing x1, y1, x2, y2, and this is some random x and this is some random y that you need to calculate, okay, based on x. Okay, directly substitute in the equation, or you can just use the formula that is shown here. This is for Celsius scale only. Okay, so the unknown temperature basically will be 100 into L minus L naught, 5 minus 2 divided by, okay, the length at 0 degrees will be called as L naught. No, I have written it as L, but this is what you take as L naught. The length at 100 degrees will be taken as L100. Okay, so L minus L naught, 5 minus 2 divided by L100 minus L naught. L100 is 22 minus L naught is 2. Okay, 22 minus 2 is 20, 20, 100 is 5 times, 5 into 3 is 15 degrees C. That is the temperature. Okay, when the length of the mercury column is 5 centimeters, the temperature is 15 degrees. So that's how the Celsius thermometer works. Fine. Let's consider another thermometer, basically the Fahrenheit thermometer. Okay. Uh, can any of you tell me on the Fahrenheit scale, what is the temperature of melting ice? When ice melts, how much is the temperature considered as? Okay, good. I got one answer as 32 degree Fahrenheit. That is correct. Okay. So at whichever temperature ice melts, see, whether it is the scientist Celsius or whether it is Fahrenheit or whether it is you or me, if you put this amount of, I mean, if you put this thermometer in melting ice, it will occupy a fixed amount of length only, no? Whether Celsius puts it in melting ice or Fahrenheit puts in melting ice, the length occupied by the mercury will be the same. Okay, provided it's the same thermometer. Fine. So when it is immersed in melting ice, it would occupy this much length. We know how much length it occupies. Fahrenheit, okay, chose to call this temperature as 32 degrees F. Fine. So that's the initial length. You can call it as L32, the length at 32 degrees according to Fahrenheit. Okay. When this same thermometer is immersed in boiling water, the mercury column would expand to a certain new length. Fahrenheit chose to call that temperature, okay, the temperature of boiling water as 212 degree F. Okay. So you can write that length as L212 if you want. So basically, whatever Celsius considered as 100 steps. Okay. 0 to 100 is 100 steps, no? 100 steps or 100 units, you can say. Okay. That same 100 units was considered by Fahrenheit as 180 units, 180 steps. So Fahrenheit broke that into smaller steps. So he got more number of steps. Okay, 32 plus 180 goes to 212. Fine. That's all. That's the difference between Celsius scale and Fahrenheit scale. The numbers are different. Fine. And you'll also learn how to convert from one to the other. Some of you may be knowing the formula already. We'll look at how you derive that formula. So we know, okay, length is the known variable x1. We know temperature y1, and we know temperature x2, sorry, length x2 and the temperature y2. And it's a fact that length varies linearly with temperature. So x and y should be linearly related. So I want you all to derive the working formula of the Fahrenheit thermometer now. Okay. You know x1, y1, x2, y2. Write the equation of the straight line. Do this quickly. When the temperature is 32 degree F, the length is L32. Okay. When the temperature is 212 degree F, the length is L212. Okay. So for a random length L, how much will the temperature be? Derive the relation between them. Fine, let's discuss the solution. See, as I said, you just have to write the equation of straight line, okay, by using the 2-point form. What is the 2-point form of the straight line? Y minus y1 divided by y2 minus y1 is x minus x1 divided by x2 minus x1. Simple. Y is temperature here, okay, the unknown value, minus y1. The first temperature that we take is 32 on the Fahrenheit scale, divided by y2 minus y1. Final temperature minus initial temperature should be equal to x minus x1. X is the known variable, length, minus the first length we know is L32 divided by L2 minus L1. So L212 minus L32. That's all. So it becomes 212 minus 32 is 180. 180 gets multiplied on the other side. And this minus 32 goes to the other side and becomes plus. So you get the answer as T is equal to 32 plus 180 times L minus L32 divided by L212 minus L32. That's all. This is the working formula of the Fahrenheit thermometer. So you are not required to remember these formulas, but you should know how to derive these. Okay? The idea is simple. They know the lengths at two different temperatures. So by using the slope point form of the 2-point form of the straight line, we can estimate the temperature at any other length. Okay, we relate temperature to length. That's the idea. Okay, hope this is clear to all of you. Now see, uh, L32 is the length of the mercury column when it is immersed in melting ice. Okay. L212 is the length of the mercury column when it is immersed in boiling water. Now, whether you call it L32 or L0 as called by Celsius, the length is the same, no? When you put the same thermometer in melting ice, the mercury column will take the same length. You can call it L0, you can call it L32, you can call it LX, whatever you want, you can call it. Okay? The length is the same. So L0 in Celsius formula is same as L32 in Fahrenheit formula. It's the length of the mercury column when it is kept in melting ice. Okay. Similarly, L100 in the Celsius formula is same as L212 in the Fahrenheit formula. Okay. Basically, that's the temperature of boiling water. That's the length occupied when immersed in boiling water. Okay. So what I'm now doing is relating Celsius scale to the Fahrenheit scale. So L0 of Celsius is same as L32 of Fahrenheit. Okay. Similarly, L100 of Celsius is same as L212 of Fahrenheit. Okay. Let us use this idea and see. Suppose you immerse the thermometer in some system. Okay, let's say the temperature is T. Or let the temperature be some X. On which scale is it X? Some random temperature. Okay. The numerical value can be different on Celsius and Fahrenheit scales. Okay. Let's say some random temperature X we have considered. At that temperature, the length will be L. Okay. At a given temperature, the mercury column will occupy a certain length. Fine. On Celsius scale, let this be some xc. Let the numerical value of the temperature be xc. And on Fahrenheit scale, let's call it xf. Fine. See, for a given length, the number shown on the Celsius scale is not same as the number shown on the Fahrenheit scale. For example, you take the first length itself, L0 or L32. Okay, L0, L32 are the same basically. Okay, they are the same length. But the numerical value of temperature on Celsius scale, it is 0 degrees. On Fahrenheit scale, it is 32 degrees. Okay. Temperature is also same, but the numbers are different. Fine. So at a length L, random length L, on Celsius scale, let's say the reading is XC. On Fahrenheit scale, let's say the reading is XF. So how will you write the formula? You will write, for Celsius, you will write XC, temperature on the Celsius scale, is equal to, what is the formula that we derived? 100 into L minus L naught by L 100 minus L naught. Okay. So that temperature XC will be 100 into L minus L naught divided by L 100 minus L naught. Okay. The same temperature on the Fahrenheit scale can be calculated as 32 plus 180 into L minus L32 divided by L212 minus L32. Right? So we immerse the thermometer in a certain system. On the Celsius scale, this is how you calculate the temperature of that system. On the Fahrenheit scale, this is how you calculate the temperature of that system. Okay. Now in the first equation, take Xc by 100. What do you get? L minus L naught by L 100 minus L naught. Okay. In the second equation, take Xf minus 32 divided by 180. Right hand side will be L minus L32 divided by L212 minus L32. Fine. Now, L is the length of the mercury column when it is immersed in this new system. Whether you mark it according to Celsius or mark it according to Fahrenheit, the length is length only, no? So basically, this whole right hand side is same in both the equations. Okay, L is equal. Okay, L0 on the Celsius scale is same as L32 on the Fahrenheit scale. L100 on the Celsius scale is same as L212 on the Fahrenheit scale. So these two basically are equal. So the left-hand sides of the equations must be equal. So what can we say? Xc, which is basically temperature on the Celsius scale, divided by 100 is equal to Xf, which is reading on the Fahrenheit scale, minus 32 divided by 180. Okay, 100, 180, 5 and 9. This is how you get Celsius temperature is equal to 5 by 9 times Fahrenheit temperature minus 32. This is how you convert from Celsius scale to Fahrenheit scale. Okay, many of you must be knowing this formula. C by 100 is equal to F minus 32 by 180, or C is equal to 5 by 9 times of F minus 32. But this is how the formula is derived. Okay, basically to relate two temperature scales, here we have related Celsius scale and Fahrenheit scale. To do such relation or to derive such relation, what we need to know is at two common temperatures, how much are the numerical values? Okay, so whatever Celsius called 0, the same temperature was called by Fahrenheit as 32. So at a common temperature, numerical values are 0 and 32. Lengths will be same anyway. Okay, at another common temperature also, we need their numerical values. Okay, whatever Celsius called as 100, Fahrenheit called as 212. Okay, so if you know two such common temperatures, numerical values of common temperatures, you can relate them. Okay, so that is one way of relating. Basically, we used their working formulas. Okay, working formula of the Celsius scale, working formula of the Fahrenheit scale. Temperatures are same, lengths must be same. So we related them this way. Okay. Now using this equation, C is equal to 5 by 9 F minus 32, you can even tell which is the temperature which is indicated same on both the scales. Okay, you substitute both of them as the same number. You will see that X is equal to minus 40 degrees C. Okay, you all must have done this already in 10th class, so I'm not asking you to solve it again. So it is also equal to minus 40 degree F. So minus 40 is a temperature which is numerically equal on the Celsius and Fahrenheit scales. Fine. At any other temperature, the number shown on the Celsius scale will be different from the number shown on the Fahrenheit scale. Okay. Like 0 degrees C is 32 degree F. Numbers are different. Okay. 100 degrees C is 212 degree F. Numbers are different. But minus 40 degrees C will be equal to minus 40 degree F. Numbers will be equal. Okay. That's the only temperature at which Celsius and Fahrenheit show the same numerical value. Okay. There is another way also to relate temperatures on Celsius and Fahrenheit scales. Now, what is the basic difference between Celsius scale and Fahrenheit scale? The starting number is different. Celsius starts from 0, Fahrenheit starts from 32. That is different. Another difference is the steps. 100 units on the Celsius scale is equal to 180 units on the Fahrenheit scale. Okay. So basically, there are more steps in the Fahrenheit scale. I must have shown more uh, like readings like this roughly. Okay, not the exact diagram, but you can indicate, I mean, you can imagine more readings, more steps on the Fahrenheit scale. So let's use that to derive the relation between them. So 100 Celsius units, okay, or steps also you can write, are equal to 180 Fahrenheit units. Fahrenheit units. Okay. So which is the bigger unit? Celsius is the bigger unit. Fine. And the starting value on Celsius is 0. Okay. Celsius starts from 0. Fahrenheit scale starts from 32. Okay. Degree C, degree F. Fine. Now, when the thermometer is kept at a particular temperature, the length shown on both the scales will be the same. Number shown will be different, but the length of mercury column will be same, no, for the same temperature. Okay. Let's say the length is L at some temperature. If the length is L at some temperature, in that length, how many Celsius units will be there? You can say, okay, fine, you cannot say it like that. Okay, let's consider a certain length like this. Or just a moment, I'll take that picture of the thermometer. Okay, when the thermometer is immersed in some system, let's say the length of the mercury column is found to be this much. Now the initial length, uh, okay, L naught or L32, L naught on Celsius or L32 on Fahrenheit, it's the same. The final length, L100 on Celsius or L212 on the Fahrenheit, that is also the same. Okay, let's call this length as L. Okay, now let's say there are, uh, how much shall we take? N1, N2. Let's say there are N1 Celsius units between L0 and L. Okay. And let's say there are N2 Fahrenheit units between L32 and L. So in the same length, N1 number of Celsius units are there, N2 number of Fahrenheit units are there. Because the unit size is different. No, Celsius units are bigger, Fahrenheit units are smaller. Okay. So the number of units will be different. Fine. So how do you estimate the temperature now? On the Celsius scale, if you want, the temperature can be expressed as starting temperature. Starting temperature is what? 0 degrees on the Celsius scale. So 0 plus how many units on the Celsius scale? N1 units. Okay, so that's the temperature indicated on the Celsius scale. But if you ask the Fahrenheit scale, what is the temperature that it will show? Starting value on the Fahrenheit scale is 32 degree F. Okay, so 32 plus the extra number of units, N2 number of units. Fine. Now, both these are saying indicating the same temperature. Number shown is different. Celsius scale will show one number, Fahrenheit scale will show one number, but the temperature of the system is the same. No, they are both showing the temperature of the same system. Okay. So these two should be numerically equal. Not numerically. How should I say? The temperatures they are indicating are the same. Fine. Now you can say that temperature on the Celsius scale is equal to N1 Celsius units. Next, temperature on Fahrenheit minus 32 is equal to N2 Fahrenheit units. We can write it like this also. Okay. Now just divide these two equations. Okay. Now we know that 100 Celsius units are equal to 180 Fahrenheit units. That is a given. Okay. So if 100 Celsius units, I'll write it as C units, are equal to 180 F units, then you can say that C unit divided by F unit is 180 divided by 100. C unit by, okay, wait, just a moment. Celsius unit is the bigger unit. Fahrenheit unit is the smaller unit. So C unit by F unit should be 180 by 100. Correct. Okay. Or you can say each Celsius unit is 180 by 100 times each Fahrenheit unit. Fine. Now the length here is same. How do I put it? Just give me a moment. We got N1 Celsius, N1 units on the Celsius scale, N2 units on the Fahrenheit scale. Okay, we can write it like this. Let's say the temperature indicated by the Celsius scale. Okay, not even temperature indicated. Just a moment. Fine. Let's consider it like this. When immersed in some system, the mercury expanded to a certain length. Okay. Temperature indicated by the Celsius scale is Tc. Temperature, numerical value indicated by the Fahrenheit scale is Tf. Okay. Now, 0 to Tc is how many units basically? Tc unit, Tc units. For example, let's say the temperature shown on the Celsius scale, I'm using some random number, let's say it is 30 degrees. So 0 to 30 degrees is how many units? 30 units. So 0 to Tc will be Tc number of units. Similarly, let's say the temperature indicated on the Fahrenheit scale is some 50 degrees. Okay, random. I'm not saying 30 degrees C is equal to 50 degree F. Let's say on Fahrenheit scale indicated is 50. Fahrenheit starts from 32. Now it is indicating 50. So how many units are there? 18 units will be there. How to get 18? 50 minus 32. So how to get the number of units on the Fahrenheit scale? TF minus 32. Okay. Now the actual temperature they are both showing is the same. Numerical reading is different, but they are showing the temperature of the same system, no, Celsius scale and Fahrenheit scale. So basically, this TC units should be equal to, okay, TC Celsius units, okay, should be equal to TF minus 32 Fahrenheit units. Yeah, if you look at it this way, you'll be able to relate them easily. TC units are same as TF minus 32. I mean, TC Celsius units are same as TF minus 32 Fahrenheit units. So let us relate them. TC Celsius units is equal to TF minus 32 Fahrenheit units. Okay. Now, Celsius unit by Fahrenheit unit is 180 by 100. So here you can write 180 and here you can write 100. Celsius unit by Fahrenheit 180 by 100. That's all. You get temperature on the Celsius scale is equal to F minus 32 into 100 by 180, which is again the same formula, 5 by 9. So C is equal to 5 by 9 times F minus 32. You can relate Celsius temperature and Fahrenheit temperature like this also, just by knowing the starting values and the unit size. Okay, like how did we derive in the previous case? How did we derive this formula? By knowing two common temperatures. Okay, the numerical values of two common temperatures. Like we took these values to derive this relation. 0 on the Celsius was called as 32 on the Fahrenheit, and 100 on Celsius was called as 212 on Fahrenheit. These sets of numbers were used to derive this relation. Okay, but here what we did was we took the starting values 0, 32, and then we used the relation between the size of the units. Okay, 1 Celsius unit divided by 1 Fahrenheit unit is 180 divided by 100. That's the relation between the size of the units. We made use of that to derive the formula. Okay, so there are two different ways in which you can relate temperature scales. Okay, let me give you another question. Now, on the Celsius scale, this length, at this length, the temperature is taken as 0 degrees. No, let us invent a new scale. Okay, on the new scale of temperature, let's say this starting temperature is 20 degree X. Means when ice is melting, the temperature on the new scale is 20x. Okay, some x units. Fine. Next, when placed in boiling water, you know on the Celsius scale, the reading will be 100. Okay. On this new scale, this x scale that is there, let's call this temperature as 420 degree X. Okay. So another new scale of temperature is invented where the temperature of melting ice is 20 units. The temperature of boiling water is 420 units. Okay. I want you to relate temperature on the X scale to temperature on the Celsius scale. Like how we derived a relation between C and F, I want you to derive a relation between C and X. Okay. Try this, all of you. I'll give you 2 minutes. Last question for today. I'll give you some hint how to proceed. Basically, you need relation between these two scales. So at some random length, okay, at some random temperature, on the Celsius scale, let's say the reading shown is C. On the new scale, the reading shown is X. Okay, we need to know the relation between C and X. Fine. So first recollect how we related C and F. We wrote the working formula of the Celsius thermometer. We wrote the working formula of the Fahrenheit thermometer. Okay. And in both the formulas, the lengths are equal. We made use of that. So try to do it the same way. Okay. Let me explain the solution. We need a relation between C and X. Okay. I'll explain the solution using both approaches. Let's write their working formulas first. Okay. For the Celsius scale, unknown temperature minus initial temperature divided by final temperature minus initial temperature should be equal to final length. See, whether it's X scale or C scale, length is length. You can call the initial length as L1, final length as L2 if you want. Okay. Or you call it L0, L100, L20, L420. It is your choice. L0 and L20 are the same. L100, L420 are the same. Okay. So Unknown length minus initial length divided by final length minus initial length. Okay, so this becomes the working formula for the Celsius scale. Next, for the X scale, unknown temperature minus initial temperature divided by final temperature minus initial temperature should be equal to unknown length by initial length divided by final length minus initial length. That's all. Divide these two. The right hand sides are equal, so the left hand side should be equal. Just equate the left hand sides. So you get C by 100 is equal to x minus 20 by 400. So this becomes 4 times. Therefore, 4C is equal to x minus 20. That's the relation between them. Yeah, Vanilla, your answer is correct. Sohan, your answer is slightly wrong, but that's fine. I think you got the idea. So this is one way of solving it. We wrote the working formula for both of them. Okay. Another way of solving it is by relating the unit size. Now 0 to 100 is basically 100 Celsius units, C units. Okay. And 20 to 420 is 400 X units. Okay. That means 100 C units are equal to 400 X units. So we got the relation between the unit size. Okay. Or you can say each Celsius unit is equal to 4 X units. That is the relation between them. Fine. Now, imagine this thermometer is immersed in some system. Celsius scale says the temperature of the system is C. Fine. X scale says the temperature of that same system is X. Basically, you're measuring the same temperature, no? One is showing it in one as one number, another scale is showing it as another number, but the temperature is the same. Okay. So what can we say? Like how many units are there here? C units are there. Okay, C minus 0. So this length includes C number of Celsius units. Okay, C Celsius units. Just a moment. So in the length from here to here, there are C Celsius units. In the same length from here to here, how many X units are there? X minus 20 because the starting number is 20. Okay, X units are there. And these two indicate the same temperature. So C Celsius units should be equal to X minus 20 X units. So C Celsius units are equal to X minus 20 X units. Okay. And we know one C unit is 4 X units. So one C unit is 4 X unit. So X can be cancelled. That's all. You get 4C is equal to X minus 20. So you can use the unit size also, starting value and the unit size, relation between unit size to relate the two scales of temperatures. Fine. I'll give you some practice problems based on this, but basically this is how you relate temperature scales. Fine. Let's quickly go through what all we discussed today. We talked about the basic difference between heat and temperature. Heat is basically a form of energy, and you say heat is the total energy of that kind contained in a system. Okay. Whereas temperature is basically related to heat contained per molecule of the system. Okay. Not the entire system. That's the actual difference between heat and temperature. Okay. Next, we talked about mercury thermometers. The basic logic behind the working of mercury thermometers is that materials expand when temperature increases, materials contract when temperature decreases. And the expansion of mercury is significantly large for everyday temperatures that we come across. Fine. And mercury is very stable also. So, I mean, mercury glass, they don't react. So, mercury will not escape anywhere or it won't react and convert into anything else. So, that system is a reliable system to show us temperatures. So, we discussed how the thermometers were designed, how the, uh, basic thermometers, Celsius thermometer, Fahrenheit thermometer were invented. Okay, we discussed that. We discussed how to relate them. And finally, we saw how to relate those temperatures to some new temperature scale also if you want. Okay. So next class, which will be tomorrow itself, we will discuss another thermometer called constant volume gas thermometer. Okay, it's an important concept. And from constant volume gas thermometer, they invented the Kelvin scale. Okay, so how that happened, we'll discuss. And if time permits, after that, we'll begin talking about thermal expansion as well. Okay. Thank you all. We'll continue tomorrow.